This is Pre-Calculus, section 1.2, day 2 notes. Today we're going to be talking about radicals. Now keep in mind, a radical is an exponent, and we're going to be talking about that more as we go on today. First, we'll begin with the definition of an nth root. If n is any positive integer, then the principal nth root of a is defined as follows. Okay, we've got the nth root of a equals b. And this means that b to the nth power is equal to a. Okay? Now, if you think about this, all right, what happens here is if we have the nth root of a, and that's equal to b, if we raise both sides of this equation to the nth power and the nth root cancel, and that's why a is equal to b to the nth power, okay? Now this is important right here. If n is even, we must have a greater than or equal to 0, and we must have b greater than or equal to 0, okay? Basically, our radicand, which is a, that is what's under the radical, and our root, that is n, okay? So what we're saying here is that if our root is even, we have to have a number that's 0 or bigger under a radical. Now think about if you have a square root of -2. We both know that, or we all know that that's imaginary, right? So that's why we are defining this as saying our radical, or our radicand, what's under our radical has to be 0 or bigger so that we don't run into imaginary. So right now, we are keeping it real, folks. Okay, so we've got our properties of nth roots, and again, these are properties that you've seen before, so hopefully you remember that. We're going to kind of quickly roll through some examples here. We've got the nth root of a times b. We can break that apart, right? So our first property is the product property of radicals, says that if you have a product under a radical, you can break it apart into separate radicals. For example, let's say we had the cube root of -8x to the 6th. Okay, now, it's okay that I have -8 under that radical because my root is odd, not even. We only have issues when we have even roots. We can take any root of, or we can take an odd root of any base, any radicand, whether it be positive or negative. So I'm just going to split this apart into two pieces, the cube root of -8 and the cube root of x to the 6th. And I'm just going to consider them separately. Well, the cube root of -8, that means what number times itself 3 times gives me -8? That's -2. And the cube root of x to the 6th, that means what term times itself 3 times makes x to the 6th? That is going to be x squared. So there we have our answer. Okay, our second property, our quotient property for radicals, says that if we have a quotient, we can split it apart into the radical of the numerator divided by the radical of the denominator. So here's an example. Let's say we have the 4th root of x to the 8th power over 81. Okay, so I'm going to split that apart into the 4th root of the numerator and the 4th root of the denominator. Sorry, that's a crazy looking 8. So the 4th root of x to the 8th, you could think of it as what term times itself 4 times gives me x to the 8th, or you could think of this in exponent form. The 4th root of x to the 8th is really going to be x to the 8/4 power, which is going to be, which is going to be x squared. In my denominator, 81 is a perfect 4th. The 4th root of 81 is +3. So we end up with x squared over 3 for our answer. Okay, number 3, we've got a radical under a radical. Well, think about our exponent rules. Remember that radicals can be written in exponent form. This is really like a power to a power. Well, remember in exponent rules, when we have a power to a power, we multiply our exponents. So when we have a radical under a radical, we're going to multiply those roots together. Okay, it's the same rule. It's just in radical form instead of an exponent form. So here's an example. Let's say we have a square root, and then underneath it, we have a cube root of 729. Okay, well, remember, we don't see it, right? But there is an invisible 2 there on our square root. So what we're going to do is we're going to multiply those roots together. It's going to be 2 times 3 is going to be our root of 729. So this is the 6th root of 729, which happens to be our perfect 6th. So our answer is 3. Okay, now number 4, if we have the nth root of a to the nth power, that's just going to give me a, okay? But there's an if here. That's if n is odd, okay? And we're going to talk about when n is even in a minute. So example, let's say we have the cube root, so we have an odd root of -5 to the 3rd power, okay? So basically this just says that our root and our power, if n is odd, our root and our power are going to cancel each other out, right? Because they're 3's, they are odd. So I'm going to write that here, n equals 3, okay? So we just end up with -5 for an answer. Now, what if our radicand wasn't negative? Okay, well, here's another example. What if we have the 5th root of 2 to the 5th power? The exact same thing is going to happen, okay? The 5's are going to cancel each other out, and we're just going to get 2 for an answer. Now, when things change is when our n value is even, okay? So again, and this, I kind of want to make a little note here, this case that we're about to talk about is only when the power and index are the same value. Okay, so if our power was 6 and our index was 2, we wouldn't be applying this rule. Okay, so this is when they're even and they're the same. Okay, so here's our example. We've got the 4th root of -3 to the 4th power. Okay, this is going to end up being the absolute value of -3, which is going to be +3. Now, if our radicand were positive, it wouldn't be an issue at all. So the 4th root of 2 to the 4th power is just going to be 2. Okay, so the absolute value is used to make the solution a positive. Or basically, as we talked about, to keep it real, okay? And this is because you can't take even roots of negative numbers, right? You can't take the even root of a negative number. So that's why we have this rule. Okay, so our rules for working with radicals. If we want to add or subtract our radicals, we must have the same radicand. Okay, so for example, 2 square roots of 2 plus 3 square roots of 2, that equals, 5 square roots of 2. That we can do, right? When we have the same radicand, square root of 2, we can add those two radicals together. When we are multiplying or dividing radicals, oh, this is different. We must have the same index, okay? We must have the same index, which again, our index is our root. So for example, let's say we had square root of 8 times the cube root of 3 in our numerator, and we had the square root of 2 on the bottom, okay? We can't multiply square root of 8 times cube root of 3. They don't have the same index. But we can divide square root of 8 by square root of 2 because those do have the same index, right? So square root of 8 divided by square root of 2 would give us square root of 4 times the cube root of 3, which would then be 2 cube roots of 3, okay? Because the square root of 4 is 2. So know when you can multiply and divide and know when you cannot. All right, let's roll through some examples here and see how we're doing on this material. All right, our first example, we've got the cube root of x to the 6th. So I like to change things to exponent form. You could think of this as x to the 6/3 power, which is going to give us x squared. Number 2, okay, be careful. We've got the same index and the same root, and they are even. So this is that absolute value case. So we don't just get x, we get the absolute value of x. That's the trick one. Number 3, we've got the cube root of x cubed y to the 12th power. So we can consider them separately. This would be like x to the 3/3, and this would be like y to the 12/3. Well, that's going to give us x times y to the 4th. Number 4, we've got the 4th root of x to the 4th. Be careful, same issue, even and the same. So that's going to give us the absolute value of x. And then we're going to have y to the 8/4 power, which is going to give us y squared. Number 5, I'm going to split this apart a little bit, okay? Now keep in mind our index here is an invisible 2. Square root of 25, that's easy, okay? We know that the square root of 25 is going to be 5. But 15 can't be nicely divided by 2. So I'm going to split that 15 apart, that x to the 15th apart, into 2 pieces. I'm going to split it apart into x to the 14th and x to the 1st, okay? And of course, then I'm taking the square root of both of those. Whenever you have a problem where you have an even index and you have an odd power, or vice versa, you're going to have to do this. You're going to have to split that base apart into pieces. So I'm going to pull out as much as I can out from under the radical. The square root of 25 is going to be 5. The square root of x to the 14th, well, that's like x to the 14 divided by 2. So that's going to be x to the 7th power. And then I'm going to be left with a square root of x, and that I can't simplify. So that's going to be my final answer on that one. All right, number 6, we're going to have some similar things going on. Okay, we've got the cube root of c to the 4th m to the 5th times the cube root of c squared. There is more than one way that you can do this. I'm going to start by breaking everything apart, and then I'm going to bring things back together. So I'm going to say, okay, I've got the cube root of c to the 4th, I've got the cube root of m to the 5th, and I've got the cube root of c squared. So I can combine those c's together, right? Because they are the same base and they are the same root. So I can say this is going to be the cube root of c to the 6th. And then I've got my cube root of m to the 5th. Now that, because 3 doesn't go evenly into 5, I'm going to have to split that apart. So I'm going to do the cube root of m cubed and the cube root of m squared, because 3 plus 2 makes 5, and 3 goes into 5 once, so that's why I split it apart that way. Now I can go ahead and I can write my answer. The cube root of c to the 6th, that's going to be c to the 6/3 power, or c squared. The cube root of m cubed, now I do have the same power and the same root, but I'm not even, so I don't have to worry about absolute value. So that's just going to be m. And then the cube root of m squared, if my index is bigger than my power, there's nothing I can do. So that's going to stay a radical. That's going to stay the cube root of m squared. Okay. All right, number 7 and number 8, we're going to have to break apart these radicals. So we've got the square root of 98. So the first thing I'm going to do is, okay, I can't add these together right now. 98 and 200, they're not like radicals. But probably I could rewrite both of them in terms of the same radical, and then I could simplify it. So I know that there's a perfect square, since I'm dealing with square roots. There's a perfect square that goes into 98, and that is 49. So I'm going to rewrite the square root of 98 as the square root of 49 times the square root of 2. And the same with 200. I'm going to rewrite that as the square root of 100 times the square root of 2, right? Well, the square root of 49, that's 7. So I have 7 square roots of 2. And the square root of 100, that's 10. So I have 10 square roots of 2. So now I can say 7 square roots of